Okay, good. Okay, we're going to start again. So I was just starting to discuss kinetics. Kinetics, of course, is impossible to avoid in combustion. I just want to say a few words about that. We're going to talk about kinetics here from a practical point of view of the people writing codes. If you write a code, you need to do something about kinetics. You cannot just say, I ignore it. You want combustion, you need kinetics. So I'm just starting talking about H2 plus O2. H2 plus 1/2 O2 gives water. That's the simplest combustion you can imagine. And you know that in practice, these things never happen. In the real world, H2 never meets O2 to give H2O. If H2 meets O2, like in this reaction, it will create OH plus OH, and this is what kinetics experts tell us. And I'm not into this business. The kinetics experts are the guys telling you, okay, this is what you need to have in your kinetics description. And they always tell you one reaction is not going to do it. They tell you you need, for example, here like 19 reactions to describe H2 plus O2. But remember that first, those things are a big success of the combustion community. All this question here, the format, for example, of these input files was fixed by the Chemkin people more than 30 years ago. We have this chance now that we can exchange all this format all over the world. And they are formatted in that way. Here you got the pre-exponential constant, the activation temperature, and here you have the temperature exponent here in the second line, second column here. The problem is those files that you can have the data, but you cannot use it for most cases. Hydrogen is an exception, which is because it's so simple. But if you go to real flames, in practice, you need so many reactions that it's almost impossible to do. The kinetics expert today, my colleague Haiwang next door, is going to be talking probably about schemes which can have 10,000 to 15,000 reactions. So there's no way you can use that in a code, okay, in a 3D code. I will show you the limits actually of what you can do depending on the number of dimensions of the code. The thing I would like to also mention here from a very practical point of view, if you don't understand anything about kinetics, is that if you have one reaction, you have three constants. At least, okay? Pre-exponential, temperature dependence, activation energy. So if you have 10,000 reactions, this thing is actually making noise, you see it. If you have 10,000 reactions, then you have 30,000 constants to specify. Oh, this guy maybe you're right. Good. Experimentalist maybe. You have to specify all these constants. Even if you believe that those guys are very good, I don't believe they can fix 30,000 constants right. I think it reaches a point where it's just too complicated. So there is absolutely good reasons to believe that from a point of view of uncertainties, trying to inject all this data into a 3D code is just a waste of time. I will talk about that probably Wednesday on what is reasonable from a CFD point of view to inject in terms of chemistry description. Obviously, it's not going to be 10,000 reactions. We just cannot do it. Okay. Actually, this thing comes from 2 years ago, but you get this guy already here. You are quite lucky to have him. You know, this Paul is actually really one of the main guys in this field. The first thing I wanted to say here is that chemical kinetics usually takes place in France. So from a CFD point of view, it really means that it's not going to be an easy computation where you could have reaction front all over the room here. Reaction is going to take place in a zone which can be of the order of 0.1 millimeter. So if you want to do a simulation of that, you're going to have to put a lot of points here. And your typical mesh size is going to be 1 micron, 10 microns maybe. So it's going to be difficult. And the structure of that, you need to understand it before you start trying to compute it. This is why theory is so important. This is why you need to talk and listen to Paul, because theory tells you in advance which kind of difficulties you're going to face when you try to solve a problem like this. So if you try to compute, for example, laminar Bunsen flame, this flame front here is going to be like 0.1 millimeters thick, and inside this flame front, the reaction zone, and Paul talked about it this morning, is going to be 1 over beta smaller than that, beta being of the order of 10 to 20. That means that the temperature profile will have a thickness of about 0.1 millimeter, and the reaction zone itself is going to be 10 times less than that. So, by the way, if you want to use a code, this gives you very useful indications on the type of resolution that you're going to need. Now, rapidly, deflagration versus detonation. Paul will talk about that. I just want to remind you that if you're trying to look at a problem where you have two states, here you have fresh gases, for example, we fill this room with gas and air, and we ignite it, there's no unique solution. It's interesting actually, combustion is not a field where you have a unique solution to the Navier-Stokes equation. You can have multiple solutions. Here you can have at least three solutions. The first solution is no flame. Okay? If no one ignites, no one's smoking here, nothing will happen. The second thing is if you start to ignite this thing, you can have a flame, which is what we call a deflagration. And if you ignite it too strongly, or for other reasons, you can go to a detonation. And you need to know the difference between the two. To understand that, again, you come back to theory. Theory is fascinating for this thing. You can write it, in a few pages. And Paul will do it probably tomorrow. You say here there's a state burnt, there's a state fresh, and you just write jump conditions between the two sides of this thing. And when you write jump conditions, you write continuity of the flux, you write continuity of momentum, and you use the state equation. You combine all of this, and you end up with a diagram which is quite famous for detonation versus deflagration. You put here the ratio of density between the fresh and the burnt gas, and here you put the ratio of pressure between the fresh and the burnt gas. And you can show that all the points should be on these two lines here. You cannot go there, you should be on these two lines. And after that, if you add here the conservation of energy through the flame front, you can show also that you should be on this curve here. And when you combine the two, you find that there are always two solutions there. One of them is what we call deflagration, where the curve is not right here because actually this point is almost on the unity line here. So it's really a point where pressure is constant. The pressure in the fresh gases is equal to the pressure in the burnt gases. Okay, if you would look at your flame, your Bunsen flame, you would measure pressure inside and outside, it's the same. And there's a second solution where the pressure is actually much larger, and there's a pressure ratio which is much larger, and this is what we call a detonation. There's also a big difference if you look at the solution of this thing, is that this thing is what we call a deflagration. It goes very slowly. Paul talked about it this morning. It's constant pressure, very low speed. So here you will have a flame front propagating at 50 centimeters per second, maybe 1 meter per second. And you need to keep that in mind, the order of magnitude, very small, very slow. And here you have something going at 1.5 kilometers per second. Okay, different world. Okay, so detonation again is not something you use in most civil applications. It's important for safety, and we try actually to build engines which use detonation today, but it's quite difficult. So that means in this diagram here you have detonation and deflagration. As I said, here less than 1 meter per second. Here, more than 1,000 meters per second. And if you want just to remember that, if you listen actually to the TV or to the radio, people get confused about these words, deflagration and detonation. They always call detonation deflagration actually, because deflagration is really a flame. So when you ignite your cigarette, you are making a deflagration, okay? No noise, it's just a flame. And detonation is a flame plus a shock, right? So detonation is really everything which you hear when you have a big explosion with a lot of noise. If your ears are killed by that, it's really a detonation. This is why all weapons typically create detonations. Just a word here about the limits of this kind of analysis. Everything I've shown you is just possible jump conditions between two states, burnt and unburnt. I'm not able to talk about the speed which will really be reached between these two states. That depends on kinetics, and Paul will talk about that tomorrow. But still important to know that there are two possible solutions to this problem, and they are very different. So you need to include kinetics, and Paul will talk about it tomorrow. Just a word here about the subsonic flames case. If you write for the low speed flames, the pressure jump here between the two sides, and you use the continuity of the mass flux, you end up with the pressure difference between the fresh and the burnt gases being equal to the flame speed square multiplied by ρ1 multiplied by 1 minus 1 over ρ2. This thing is negative. And if you look at a typical laminar flame like this one, that means the pressure difference between the fresh and the burn is 1.1 Pascal. Okay. Which really means you can say pressure is constant. This is what we're going to be using for all theoretical work. Constant pressure is a very good approximation. Which means also that if you want to solve now the state equation, you can say that P1 over P2 is equal to 1, so the product of rho by T is going to be a constant. And for many theories, that's going to be useful, and Paul is going to use it actually tomorrow. Now, as I mentioned before, planar flames just don't exist in practice. The end of this small experiment. And from a scientific point of view, it's extremely important to know how you can go from one situation to the other. Why do you go from one situation to the other? Now, one of the things which happen in a system like this is that you start with a flame which is going slowly. You will see here an experiment which is installed in Australia, where they have this small box, well, small is half a meter long, which is closed everywhere except at the outlet here, and you ignite the flame here, and here you have grids which are supposed to mimic chairs or tables or things like this. And you will see that the flame initially, when there is no obstacle, the flame will be ignited here and will go in this direction. This flame will be slow and laminar actually. It will go to at a speed of the order of half a meter per second. But as it would touch here these things by mechanism I will explain Wednesday probably, it will get faster and faster, and it ends up going out here at a speed of the order of 300 meters per second. And if the tube was longer, it would actually go to detonation. And so it really shows that this business of transition here from deflagration to detonation is also controlled by turbulent motion. So you see the flame here starting, this blue zone, very nice laminar spherical flame. Now it's touching the first obstacle, it's getting wrinkled, more and more wrinkled, and then suddenly you get this acceleration. Okay. Being able to predict these things is a critical question in the community. Now, if you wait long enough, if this tube would be long enough, and if you have a detonation, and then of course a lot of things can happen. When you go from deflagration to detonation, this is something which happens in piston engines. If you go to deflagration to detonation, it's one cycle only, okay? And that's the end of your engine. Because the pressure in an engine goes to of the order of, the maximum pressure may be 80 bars, 90 bars in your engine. If you go to detonation, it's going to be 700. So the piston just dies right away. This is what you call, well, people call it knocking. It's not knocking, it's super knocking or wumble if you want. This is really something you don't want to have, and you have it in engines today. Certain engines go into this kind of detonation regimes, and that's the end of the engine. So in this course here, really we want to focus on deflagration. Okay? Paul will be talking about detonation. You'll have enough of detonation in a few days, so I'm not worried about that. And what we do in a gas turbine or in an engine is we focus on deflagration. Normally, we should stay in this regime. So flame regimes, since we talk about flame regimes, you know, since I've mentioned it before, to get combustion, you need A, B, you need fuel, oxidizer, and temperature, which really means you can have two types of regimes. The first regime is to have premixed gases. We'll call it premixed regime, because we mix A and B before we ignite. So these things are just waiting for temperature. And then we have diffusion flames where we don't want to store these things together, we store them separately, and so then we have a diffusion flame. Premixed flames is really what Paul is going to be talking about, and I will need to talk a bit about diffusion flames. Those are the basic two prototypes on which we can develop theory and which we need to understand to do combustion. By the way, these flames are much more efficient than those flames, okay? And they are much more dangerous. Because if you mix A and B together in a bottle, you just need a spark or any small event, and then everything explodes. So we don't want to do that, except that for efficiency, those flames are much better than those ones. So it means also that if you go to industry, in practice quite often, we know that there's a number here, which is the stoichiometric ratio, 1, which splits the world in two. On this side, you get the lean flames, and those lean flames are good because you don't put a lot of fuel there, so the pollution levels are better. If you put too much fuel, then you get a rich combustion, you start producing CO. CO, 0.4% is sufficient to kill you. Okay? It's not like CO2. CO just kills you much faster. But by the way, you cannot do that with your car anymore. Okay? You used to be able to kill yourself by breathing the exhaust gases of your car. There's no CO left now, so if you breathe the exhaust gases of your car, you're going to drown in CO2. It's going to take a long time. CO was much better. It was actually a problem for GM because people tried to commit suicide 30 years ago, and they actually sued GM because they couldn't kill themselves. So it's complicated to sell something in this world. And of course, you're going to have CHX, you're going to have soot and all these things. So basically, you should be on this side. The problem is that's also something that theory tells us. You cannot go very far on that side because there's a lean extension limit for a premixed flame. If you're going too lean, then the flame just stops. You cannot decrease the amount of fuel you put in the flame as low as you want. At some point, this thing will just quench. That's what you call the lean flammability limit, and that's the same thing on the rich flammability side. But usually we don't need to go there. We are not rich enough to pay for all this fuel. But this limit is a tough limit for many applications. Premixed flames, as I said, dangerous but efficient. Diffusion flames, less efficient but safe. Just to give you an example, and this is the same burner. Here you have a jet. Either you inject here pure gas, or here you inject a mixture of gas and air. You have a typical premixed flame. Here you have a diffusion flame. Usual features of this thing: the premixed flames are blue, short, intense, stable. The diffusion flames are lazy, long, and yellow. And if you listen to what is a flame, you remember that they are yellow because of soot. Okay? Soot is black normally, but when it's hot, it's yellow. So if you have a flame like this, it's not good. Okay? This is going to pollute too much. So we want to be on that side. So in practice, what we want to do, we want to store reactants separately for safety, which will lead to a diffusion flame, but we want to burn them in premixed mode, which will lead to premixed combustion. So the way to do that is that we need to store them separately, and then we need fast mixing. And this is where combustion interacts with flow. It really means that when you talk about mixing, you don't talk about combustion, you talk about mixing stuff. So it's really a way that you need to shape your injection systems to mix fast. So this is, I'm coming back here to my injectors. If you look at the injection system of a gas turbine or of many burners, they are very complicated because their goal is to mix air and fuel as fast as possible. We don't want to mix them before. You could say, oh, why don't we put a bottle here 1 meter before and fill it with premixed gases? If you do that, you're going to die at some point, because if the flame flashes back here, it's a bomb. So we try to mix at the last moment, last minute. So this system is extremely critical because this is the place where you want to mix things as fast as possible. The way you do that is usually to add swirl, to increase turbulence, to shake. Exactly when you prepare a cake, you shake all the ingredients together as fast as you can. Now the problem is that often when you do that, you have a mixing which is not sufficient here in the chamber, and you start doing diffusion flames. So you start having these yellow flames. So you have soot, you have NO, you have all these pollutants that you don't want. So one of the things you do, you add here, for example, a mixing tube. This tube here was not there in the initial design. The engineers added it because their NOx levels were not good. So they've put this small tube here, and the objective of this tube is to give a little bit more time for air and kerosene to mix before you go into the combustion chamber. The problem is that I'll come back to these notions during the lessons of diffusion flames, is that if you have the initial design here, you have the stoichiometric line, which is here, and on the stoichiometric line, you're going to have very high temperature, and you're going to produce a lot of NOx. If you add the premixing tube, the idea is that you will mix things first, and the flame will be sitting here outside, and then because the flame now will be mixed, then you will have low temperature and low pollution. And the problem is to be able to know how you go from this kind of flame to this kind of flame in practical systems. And of course, like I said before, flames never do what you expect. So this is what the engineers expect, and this is what happens quite often, because if the flame sees that there is something to burn here, it can flash back. That's the term we use. That means it can go to a place where it shouldn't go. And when you have flashback, then again, that's the end of this thing. Okay, I want to go now to another definition of the flames we're going to face. This one is based on the confinement problem, on the geometrical problem. we can basically split flames in two big categories: unconfined flames and confined flames. Unconfined flames, as you would expect, is a flame in a free space. There's nothing going on, there's no wall. You don't have to worry about the shape of the chamber or anything. And confined flames, it's much more complicated because you need to take into account the fact that the flame is taking place in a geometry with walls everywhere. And in practice, unconfined flames, I made a joke about the utility of laminar flames. There are not many applications for laminar flames. There are applications for unconfined flames, a few of them. One classical one is flares. You get these huge flames. You've probably seen there near refineries. You get these huge free flames, which are there only to build the additional gases that the refinery system cannot handle. If the pressure goes too high, they have all this gas. So what do they do with it? They just burn it, which is stupid. Okay, but you talk to them, they will tell you there's nothing else you can do. Just burn it. So that's one example where a free flame is useful in some sense. It's just for safety. Just want to blow the gas away. But in all other cases, flames, if they are unconfined, they are not useful. Because if you want something out of a flame, it's either you want heat, so you have to put the flame in a box where you recover the heat, or you want propulsion, you want power, then you have to put it in the combustion chamber where you can recover the propulsion. So in most flames, you have to be confined. Now, to study these things, you can basically see what's going on. In the academic world, we study only unconfined flames, and in the industry, we study only confined flames. So that's a big split in the community. You go in the academic world, you see these Bunsen flames, you see these free flames, and you go, for example, to Sandia, you get this TNF workshop where we study all kinds of free flames in the free atmosphere, and this is really useful. But if you go to industry, they will tell you, well, it's not a useful flame for us. It's useful for academic studies, but for us, we want to see a flame in its combustion chamber. Now, it's not only an academic problem. If you're doing a CFD code, you see why the rate's going to be very different. Because if you're doing an unconfined flame, you're going to do this kind of mesh, okay? It's going to be IJK cube. Maybe if you're sophisticated, you do it in cylindrical geometry, but the mesh, the code you're going to be writing is an IJK structured code. And it's much easier to build a code like that than it is to build a code for unstructured meshes, which can handle any geometry. And it's a major difference also here. The DNS community has been working here, and the WANS community has been working here. Why is it so? The DNS community wanted to be precise, so they wanted structured code. The WANS community wanted to be able to handle the geometries of industry, so they had to go to unstructured code. And again, in the middle, we have to decide how we're going to do LES. And you're going to see it's a big issue. As I said, DNS is usually performed in these very simple boxes, and you can do very nice, simulations in these kind of boxes. And you can even do this kind of flames, which is again an unconfined flame, computed here by John Bell. And but again, all these flames are unconfined, so the geometry is very simple, and the mesh, as you can see, is extremely simple. Same thing here by the group at Sandia, Jackie Chan. You have here the instantaneous flow, you have the mean flow here, but again, the geometry is extremely simple. If you want to go to this animal, you have to change code. When I say change code, you take the first code, throw it away, and you start from scratch. Because there's just no way you can adapt these codes to do this kind of geometry. You need to build a code from scratch. So during this course, I really want to focus on the codes which are useful for confined flames, for real flames. And I will talk about what we need to do for turbulent combustion models for that. And I will also talk about instabilities. As you've seen, instabilities are quite important. And first, I will need to go into basics because we need them to build the models. The second thing I want to do before we go to that is to talk about complexities. You talk to Hai Wang, actually, who is talking right now. He's going to tell you that what he's doing is complex. And what I'm doing is complex too. So we have to define what we define by complexity. Of course, if you look at a flame like this, a Bunsen flame or just the lighter for your cigarettes, this is very complicated, and it's basically complicated because of chemistry. chemistry there, flow is simple, chemistry is very complicated. But the geometry is simple, the flow is simple, and we only have to care about the flow. So this is what the academic community calls complex. Okay? This is what I call complex. Okay? And you see the difference. The difference is that we still have complex chemistry. Those guys are burning the same thing that we burn. It's CH4 or some kind of fuel. But then the geometry now is not the same. It's confined flames, unstructured meshes. The flow itself is very complicated. High Reynolds number, complicated turbulent flow. And here we cannot only look at the flame. We need to look at the temperature of the walls because it will change the place where the flame will be stabilized. We need to care about radiation. We need to care about multiphysics. So all of this is complicated. I'm not saying that those guys here are doing simple things. Okay, I'm just saying that what we do is even more complicated. Okay, it doesn't make our life easy. So let me just show you a rapid sample of codes that you can find in the community. The first codes you can find in the community is what we call zero-dimensional codes. You take the equations that Paul was showing this morning, you remove all dependence with space. You say it's a box here which has completely no variation in either direction. So all the grad, you take them away. You're left with only these two equations. The temperature grows because of heat release, and the fuel mass fraction and all the species mass fraction change because of chemistry. You can have as many reactions as you want here. You can have 10,000 reactions. Why? Because it's a one-dimensional problem in time only. It's easy to solve. It's not easy. I shouldn't say that. My colleagues will get angry. But it's not that difficult to solve. Okay? There are codes which do that all over the place. It's a little bit complicated when these equations are stiff and you have maybe 1,000 to solve. But it's quite doable. The only thing you need to be careful about is you need the right kinetics here, and you need the right thermochemistry to tell you what Cp is, what the density is, and all that. But that's easy to do. And the thing you do usually is this kind of problem. It's what we call auto-ignition times. So what is the auto-ignition time problem? The typical one is the following one. You take a box, this room, you put fuel and air, and you ask yourself, how long do I have to run to the door? Okay. If it's room temperature, I can take my time. Actually, I should take my time, because if I run and I make a spark, then it's going to be difficult. But if I don't make any spark, I could take 2 years to get out. It's not going to be a problem. But if the temperature in this room is 400 K, 500 K, 600, at some point you say, oh, maybe I should go faster. And so this is what these codes are doing. They give you what we call the auto-ignition time. If you plot here the time, if you put the temperature, you see for a long time nothing happens, and then usually, and again that's a specificity of combustion, when it will start burning, then you have to start running, because it will happen very fast. And the curves are always like this, and here this time it's called the auto-ignition delay time, and the auto-ignition delay time can be computed with these tools as a function of temperature. Usually we plot it as a function of 1 over the temperature. And so you see here the temperature is high, the ignition delay is small, and this is the log scale. And here you go to low temperature, the ignition delay grows like the exponential of that. So at room temperature you can wait 2 years, nothing will happen. And if you go high in temperature, you see, for example, 1,000 over T is 1, that means the temperature is 1,000 K. The ignition time will take 10 milliseconds. You have to run. Okay? And this curve can be measured experimentally in a shock tube system, and Van Hansen does that also all the time. And it can be computed with all the sophistication you want in the chemistry. And all the kinetics community does that all the time. Okay? So this is one classification, one example of CFD code. And it's really important to say that this is where the kinetics experts stop. Okay? They never compute what we call a flame. This is not a flame, okay? It's an auto-ignition problem. As soon as we want to compute a real flame, like these guys here, a flame in which you have a dependence with space, that means you need to add now transport in this problem. You need to add diffusion of heat, diffusion of species, description this morning, Paul talked about the fixed law and all these things. You need now to add that to all the things you had before. And then, by the way, this kinetics expert, they tell you, not my problem. Not my problem. The flame guys, what we call the flame guys, is us basically. We have to find a way to make flames. And what we see quite often is that the schemes which are used for that, if you try to plug them in the flame code, it doesn't work. There's no reason for that. These guys have tuned 30,000 reactions to mimic that. So probably they got one wrong or something, and then when you don't see it on this problem, but you see it in situations where all the species are diffusing, and then the details become important. So those of you who are working on flames probably know that the most difficult thing to do when you want to compute a 1D laminar flame like this one here, stagnation point flame, is to get the first solution, to be able to converge this thing, because you have typically 1,000 species, you need to find an initial guess for them, and usually if you don't find the right guess, it just explodes. So it's a very difficult game here. This is why we need to simplify the chemistry. But still, this is a very simple flame, okay? The next step is to do multi-dimensional laminar flames. Here, instead of having only a planar flame, you have a flame which depends on X, Y, and Z. So typically here, a Bunsen flame. So you need to add some fluid mechanics here. You didn't have to do that here. Usually here we impose the flow. For example, we say it's either a planar flame or it's a stagnation point flame, so we don't need to solve for the flow. If you do a flame like this, you need to solve for the flow. So things are getting a little bit more complicated. And then suddenly we change. We move from laminar to turbulent flame. So by the way, here uncertainties are going up quite strongly. So here we need to add turbulence. Turbulence should be big actually in this plot because it's a big complication. But it's not sufficient. If you want to compute a flare, like this guy here, you definitely need radiation. When you have a flare like that, the temperature on the ground here is so high that the ground will actually melt. So this is what kills people actually. If you are standing here, it's radiation is going to kill you. And of course, if you want to compute radiation, you need to compute soot, because it's really the soot which is emitting most of the radiative flux here. So you see, by the way, the difficulties are going up, because the chemistry for soot, of course, is much more complicated than it is for the gaseous phase. And after that point, up to now, I was talking about unconfined flames. Now I need to talk about confined flames. If you go to confined flames, then things, as I said, change. You need to rewrite the code. You need to be able to compute the geometry. If you cannot compute the geometry of your chamber, it's finished. So here, basically, you change your code, you take another one. Which one is up to you? We'll talk about that in the next days. So that's very strong, a very strong statement, because that really means that you need to change what you had before. So this is an example of confined flame. Here you have the injector, you have the blades here, so now you have to talk about the confinement. And by the way, acoustics come into the picture. Acoustics for a free flame, if you have a flame like this one, the only thing which happens is that acoustics are going away, it makes noise, you can hear it. But if the flame is confined, acoustics cannot get out, so what they do, the acoustic waves are bouncing on the walls, coming back into the domain, and they may generate instabilities, acoustics, as I've defined half an hour ago. Now, as soon as you've done that, even if you can handle that, all these things, you need to worry about heat transfer. I'll talk about flame wall interaction probably Thursday. This is an example of a helicopter chamber. There's a name here, you cannot see it, it's confidential. Just what you see here is the temperature measured. The way you measure temperature in those systems, you have a paint, you paint the chamber, and this paint changes color depending on this temperature. So you run the engine, then you open it, and you can see, for example, here, this is hot, too hot here. This is cold, it's okay, heat's too hot, etc. And all the small things you see here are holes. They are what we call multi-perforation holes. And if you change one of them, you can kill the chamber. And really, you need to compute the combustion and the cooling system together because they are coupled if you really want to compute the chamber. If you go to Turbomeca or to Pratt & Whitney or General Electric, you tell them you're going to compute a combustion chamber and you don't know how to handle the multi-perforation, they're just not going to talk to you. Say, come back when you know how to do it, because this is as important as combustion. So it's one more element that you need in your solver. Now, these structures may not have to be fixed. You can have vibration. This is in a rocket engine, for example. You can see this part here, which is a part of solid here. It can actually start moving. So that means quite often you have to care also about fluid structure interaction. Once you know the temperature of the walls, by the way, you look at the stresses there, and it could be also looking at the vibration of these things. So you see the picture becomes much more complicated. Now, because you have all these things together now, you can see that kinetics or the details of one of these things Everything is important, okay? But if you want to go to the finish your computation and not explain how complex it is, you have to make choices. And this is where things are difficult. I just want to show you the next slide, which shows you also the same thing seen by the point of view of CFD guy. The CFD guy will tell you, I don't care about that, those are just the equations. What I want to know is the following. What is the mesh type? What is the spatial order of my method? Which kind of method are you going to use? Which is the time integration? What are boundary conditions? How do you handle the massively parallel computing necessities of today? Are you able to maintain your system on the future computers? How do you do the coupling? If you have multiphysics, for example, how do you couple things together? And you see now, if you want to write a code and if you want to use a code in your PhD, you have to face all these questions. You have to face actually the last one, which is, as I said before, you need to use that to do optimization. You need to use this thing to quantify the uncertainties and to do data assimilation. I will come back to these questions later, but quantification of uncertainties is really the major issue here. Because you have so many models assembled together, at the end of the day, you should ask yourself, okay, do I believe in this computation, or is it just, a game? Okay, colorful fluid dynamics, as I say. And for the combustion community, being able to quantify the uncertainty on your results is a critical question today, because a lot of people don't believe in the simulation. There's a rule in France, for example, today, that you cannot certify an industrial installation in terms of safety by using 3D CFD. It's forbidden. The reason for that is that they have found out over the last 20 years that the results of the CFD codes were just so random that you could not rely on them. Just they say, no, it's forbidden. Which is strange, because the way they do it now is just by 1D correlation, which is stupid. And so any 3D code is better than a 1D simulation, but they've been so shocked by the fact that CFD was giving bullshit, basically, that they don't want to see it anymore. Which is bad for our community, okay? Because when you reach that point, people might say, let's stop CFD. There are people in industry, in gas turbine, for example, who say, we should just do tests, not CFD. And CFD is not precise enough. It's a major problem today that if we keep doing simulations which are just not precise enough, no one's going to believe in that. And for people working in industry, I'm sure they know this problem, that you go to your manager, you show the computation, the guy says it's nice, but is it right? Can I believe it? Well, that's a tough question. So, I'd like to quote someone here who was actually one of my masters in combustion. The guy was called Peter O'Rourke. He's the guy who wrote the Kiva manual probably 30 years ago. And the first line of this Kiva code was to say, don't be a perfectionist. If you want to do combustion, if you're a perfectionist, you're never going to go anywhere. The big problem is to find the best compromise between all I've said and not to focus on one action only. And for example, you don't want to focus on the phenomena that you know because you know them. It doesn't make sense. You have to focus on the weakest link. It's like a chain. If you have a chain and you have one weak link, the whole chain is as good as the worst link here. For example, if you are very good in kinetics and numerical methods and radiation and you are very bad in heat transfer, the overall result is bad. So it's don't spend your PhD on focusing on that all the time. Don't put all your energy on one point only. If you're interested in the overall result, you need to make sure that all the elements are right. And that stuff, it's difficult. So I just want to show you how subtle this can be. Because the problem is to know where is the weakest link, okay, in your chain. If you're looking at rocket combustion and you're doing computation of H2O2 engines, which is something which is very important for France at the moment. We use that to propel the Ariane 5 engine. So you have an engine where you inject hydrogen and oxygen. This thing burns so fast that you can say that chemistry is infinitely fast. And again, this is, theory tells you that. And the theory, by the way, gives you a way to solve this problem. You can say that chemistry is so fast that you can use a theoretical model to handle chemistry there. And you can give very nice results for this problem. And in this case, the weakest link is not kinetics, because kinetics, you can say it's infinitely fast. And you can do this kind of computation here, which is an example here where you are injecting liquid oxygen and hydrogen, and you can see the flame. And this model uses the assumption that chemistry is infinitely fast. And you talk to your customer, and the guy says, I'm happy with you, but I want you to use CH4 now instead of H2. Okay, if you don't know what you're doing, you can say, I'm going to run the same code. Well, except that CH4 is much slower than H2. And so suddenly, the weakest link, which was not chemistry, becomes chemistry. And if you don't know theory, or if you don't know anything about the details of combustion, you're just going to run the same code, except for CH4 flame. The flame is not going to be starting here. The flame is going to be lifted. It's going to be anywhere downstream of this thing. And so suddenly, the weakest link becomes chemistry. So you need to solve for chemistry. But solving for chemistry now is becoming a huge problem in itself. You need to account for complex chemistry. And so what was simple for H2 becomes very, very difficult for CH4. And again, if you don't know the basics here of the physics of combustion, you're going to get lost right away. And of course, by the way, it takes some strength to go to the customer to tell him H2 was easy, but CH4, sorry, it's tough. So what does it give for CH4? For CH4, I'm going to show you the computation I've shown you before. We can do only the computation of the lip here. And this is what it gives. You have here H2 and O2. Actually, we did it for H2, we didn't do it for CH4 yet. But you see the flame here, when you get the details, as I mentioned before, you have here a micrometer, and you see the turbulent structures here. And this is resolved chemistry now. It's not saying infinitely, chemistry is infinitely fast. And the cost of this simulation compared to the other one is 100 times more. So it really tells you that defining where the weakest link is the big problem for you if you want to compute a real system. So if you work in industry, obviously you have no choice. You want to compute a real system, so you have to pick up your choice here to know what's most important. If you do a PhD, sometimes you can focus on one of them because your boss said you work only on the transport equation or you work only on kinetics. But after that, even if you do your PhD on that, I really recommend that you start looking at the whole picture. Because otherwise you remain one method man, one problem man. It's not combustion. Combustion is really all of that together, especially in CFD. You need to handle all of these things together. So I guess we're going to take another short break, 10 minutes, and then I will start going into the equations.